In this video, we're going to explore this formula here that converts Celsius into Fahrenheit, and at the end of this, we'll hopefully have a justification on why solving equations for variables might be an important skill to have. So first, we know this formula here. The Fahrenheit temperature can be, or is equivalent to 1.8 times the same temperature equivalent in Celsius plus 32. So what we want to do is to use this formula. This is the equation that allows us to convert from one temperature to the other. We want to find the Celsius temperature for 98.6 degrees Fahrenheit, 102.3 degrees Fahrenheit, and 36.8. This is a review. These first three examples here are a review. So what can I do? I can take, if I know what F is equal to, 98.6 degrees is F. That is the temperature in Fahrenheit. So in my equation, where I have Fahrenheit equal to 1.8 C plus 32, I'm going to plug 98.6 in for F. That is the value for Fahrenheit, and what I get is a one variable equation that I can solve. Also a review. So the first part is kind of evaluating, plugging values in for variables, and now we have an equation that you should be able to solve. And to do this, I'm going to use my the reverse order of operations. So think about my properties of equality. I know I can subtract 32 from both sides, and that will leave me with 1.8c on the right, and 98.6 minus 32 is 66.6 degrees. And now I can use this division property of equality. I can divide both sides by 1.8, and what I get on the left is 37, and on the right is C. So this is 37 degrees Celsius. 37 Celsius. And what we just did there was convert 98.6 into Celsius. We can do the same thing for the next temperature. And if you want to pause this video and try it, you can go ahead and do that. I'm going to plug 102.3 in for Fahrenheit. I'm going to repeat those same steps. So I need to subtract 32 from both sides. And if I put that in the calculator, I get 70.3 equal to 1.8, and I can divide that by both sides by 1.8, and I get my temperature to be 39.1. It's approximately. So we get approximately 39.1 degrees Celsius. And the final example will be to convert 36.8 degrees Fahrenheit into Celsius. So I'm going to plug that in for F. And if you want to pause the video and do it yourself, you're welcome to. But I'm plugging this in for F, and I'm going to solve this for C. So I went ahead and solved this for C, and I followed the same steps. I subtracted 32 from both sides, and then I divided that quantity by 1.8, and I got my final value of 2.7. So 36.8 degrees Fahrenheit in an equivalent Celsius conversion there, temperature is 2.7 degrees. Now let's think about if we notice a pattern. In each one of these, we're going from Fahrenheit, or from Celsius into Fahrenheit. And what are we doing each time? Each time you notice that we are subtracting 32. So we're starting with our Fahrenheit value, and we subtract 32. We did that. That was the first step in each one of these equations that we were solving. And then we took that and we divided that quantity by 1.8. And what we were left with was our solution. So let me see if we can generalize this. We took our Fahrenheit value, we subtracted 32, and we took that whole thing and we divided it by 1.8. And that gave us our Celsius. What we just did right here is rearrange this formula to solve for Celsius. Now, why might this be important to do? Well, think about if we had to convert a list of 100 temperatures from Fahrenheit to Celsius. What you would be doing is literally what we just did. And if we were just using this formula, we would have to plug in Fahrenheit, subtract 32, divide by 1.8. And that's a series of steps to do 100 times. So what we might do instead is program an Excel sheet or some other computer software to take values and convert them for you. But in order to do that, you need to do what we just did here. You need to rearrange the formula and solve it for Celsius. So now if I give you a value like 99, 99 goes right in here. We'll subtract 32 and divide by 1.8. Now you might be asking, how did we get this, or how could we get this? So let's go to the next page and show you how we could get this value differently. So here's our formula, and we looked on the last page, we looked at how we could rearrange this to solve for C, and we used the pattern that we saw developing. But we don't actually need to do that. We don't have to do 3 or 4 or 5 examples, notice a pattern, and then jump into the generalized form. What we can do instead is actually use just the properties of equality. We don't have to plug anything in for F in order to find C. In other words, we can isolate this value of C just like we did when we were solving one variable equations. And to do that, we want to get C by itself. How can I do that? Well, I want to subtract 32 from both sides. That would eliminate this positive, or plus 32. And I know I need to do that to both sides of the equation if I want to keep this equation to be true. What am I left with? Well, we know on the right-hand side, we just get 1.8c. On the left-hand side, in previous examples, this would simplify to something. Typically, it's simplified to something. But here, it doesn't simplify to anything. And in fact, we can just leave it as f minus 32. That's the only way that we can write this right now, is just to have f minus 32. And now what I can do is divide both sides by 1.8, just like we did when we were solving one variable equations. We used the division property of equality. And what am I left with on the right-hand side? Just c. And what am I left with on the left? Well, there's nothing really to simplify here. So we can just leave it as f minus 32 divided by 1.8. And if you want to make it a little bit more clear, we could put parentheses around the f minus 2, or f minus 32. And that's what we get. We get this formula. We solved it for C using our properties of equality. Let's look at one more example. In this example, we are given this formula that includes the variables t, b, n, r, and h. And you can see what each one of these represents. T would be the total number of milliliters. If we're giving a patient a bolus, B would be the number of milliliters in that bolus. N would be the number of times it was administered. R would be the rate that an IV pump is running in milliliters per hour. And H would be the number of hours that that pump has been running. So when you multiply B times N and add that to the product of RH, you're given the total number of milliliters that the patient received. Now, depending on the situation, you may want to document in a spreadsheet or something, and you may need to do calculations over and over again. So what we might want to do, and what we want to do in this example, is to isolate H. We want to get H by itself. So what can we do? Well, think about what we did in previous examples, or what's happening here. We're taking Bn and we're adding that to R times H. Now, if we wanted to work backwards, we know addition and subtraction, we need to eliminate this Bn quantity first. So that's the first thing I'm going to do. I'm going to subtract a value of Bn from both sides. I know that looks a little weird, but it's just like if this was a 5 or a 7 or a 22. We would subtract that quantity from both sides. On the right-hand side, we would be left with just R times H. And on the left-hand side, there's nothing to simplify. So I can only write the difference here, T minus B times N. And then finally, I need to isolate H. I need to get rid of this value of R. R is being multiplied, so I want to divide both sides by R. And what does that leave me? On the right-hand side, I'm left with my quantity H. And on the left-hand side, there's nothing to simplify here. I can only write this as this difference, so T minus Bn divided by R. And this is how we can use the properties of equality to solve for variables in a formula.